Hello. In this video I'm going to demonstrate procedures you can use to obtain regression output in SPSS and how to interpret that output. Included is a discussion of various options that are available through the basic regression module for evaluating model assumptions. The video will necessarily be kept short, so if you are interested in a deeper dive into interpretation of the output and so forth, then please be sure to download the PowerPoint underneath the video description. The PowerPoint includes citations as well. A copy of the data will be provided as a link as well underneath the video description, so be sure to download it if you want to follow along. And I'll also be including a document that contains links to other videos based on this example and data. So if you find the video and supporting materials helpful, please take time to like the video and share it with others, and also please consider subscribing to my YouTube site. So let's go ahead and look at our example. So in this particular example, what we're going to be doing is regressing measures of student achievement onto measures of performance goals, mastery goals, interest, anxiety, and their gender identification. So the achieve variable, which is the dependent variable, is continuous, as are the independent variables performance goals, mastery goals, interest, and anxiety. Gender identification is a binary independent variable, and it is demicoded 0 and 1, and it is permissible to include binary independent variables in a regression model, but making sure that you demicode it to help facilitate interpretation of the intercept within the model. So this is the basic model that we're going to be running. This is just a diagram that I drew up using the Amos program just to kind of give you a visual for what we're doing. So just before we actually get into sort of a real-time demonstration, I just want to show you some of the screens that we're going to be working with to run our analysis. So you'll see that we're going to go to Analyze, Regression, Linear. You'll see that the box to the right opens up and we put our dependent and independent variables into the box. We'll be clicking on the Statistics tab to request confidence intervals, part and partial correlations, collinearity, diagnostics, and so forth. Under the Save tab, we have options for saving predicted values, residuals, influence statistics, and distance measures. And these can be useful for identification of possible outliers in your data, as well as cases that may be influential in terms of your regression model. If you click on the Plots option, you can obtain residuals plots. In this case, I'm requesting a studentized residual, a plot of studentized residuals where they are plotted against standardized predicted values. We're also asking for standardized residuals plots that include a histogram and normal probability plot, and then I'm also asking for partial plots. So at any rate, before we kind of get started looking at interpretation, let me run the analysis or go through those steps in real time using SPSS. So here is our data in SPSS. We have performance goals, achievement, mastery, interest, anxiety, gender identification. This last variable is not going to be included. So what we're going to do is go to Analyze, Regression, go to Linear, and we'll move Achieve over to the dependent box, performance goals, mastery, interest, anxiety, and gender identification to the independent variable box. Under Statistics, I'll ask for confidence intervals, as well as collinearity, diagnostics, and part and partial correlations. Although I don't demonstrate it in the PowerPoint, I'll go ahead and click on descriptives as well, and we can also ask for case-wise diagnostics if we want. Under Plots, I'm going to click on S residual, or this is basically studentized residual, and move it to the y-axis, and then Z PRED for predicted. So basically the standardized predicted values, move it over to the x-axis. We'll click on Produce All Partial Plots, Histogram, and Normal Probability Plot. Continue. Under Save, we'll click on the unstandardized predicted values, the unstandardized, standardized, and studentized residuals. We'll click on Mahalanobis distance, Cook's D, and we'll go ahead and click on some of these influence statistics right here. So we'll click on Continue and then OK, and so now we get our basic output file that contains all of our information. So you can see we have our descriptive statistics, correlation matrix here. That's again from clicking descriptives. As we scroll down, we get our model summary table and ANOVA, which is basically, these two are used to evaluate the omnibus effect of the independent variables on the dependent variable. Under the coefficients table that we have right here, you can see we have the unstandardized regression slopes, or partial regression slopes. So there's performance goals, mastery, interest, anxiety, gender identification, and we have our standard errors for those slopes, as well as t-values and p-values that are given right here. Next, you can see that we have our standardized regression coefficients right here. In this portion of the output, we have 95% confidence intervals. If you want to change the confidence interval, you can do that, but the default is 95%. Here, under correlations, we get the zero-order correlations, partial correlations, and part correlations, and collinearity statistics, including tolerance and variance inflation factor. As we scroll down a little bit further, you can see that we get, again, case-wise diagnostics, a little summary table of the residual statistics, and then you can see we have our histogram of the standardized residuals, which can be useful for evaluating normality assumption concerning the residuals. We also have a normal probability plot for the regression standardized residuals. Again, this can be useful for evaluating the normality assumption. Down below, we have the residuals plot, where we have the studentized residuals plotted against the standardized predicted values. So this can be useful for evaluating several things. First, we can look for the possibility of outliers, particularly in reference to our conditional dependent variable. We can also evaluate for the presence of heteroscedasticity in terms of the residuals. Homoscedasticity of residuals is an assumption of the procedure. So if there's heteroscedasticity, that can introduce various problems with respect to your statistical tests. We can also look for possible nonlinearities and so forth. So this is really, this plot right here is a really useful one for evaluating several different assumptions in the context of regression. Then finally, we have our partial plots that are given below. Okay, so I'm not going to spend a lot of time diving through every part of the PowerPoint, so I'm just going to hit the highlights. Again, if you want more information, you can just download the PowerPoint and peruse it at your leisure. But first off, in the model summary table, you can see that we have the R, which is the multiple correlation. It's basically the correlation between the set of independent variables and the dependent variable. We have the R square value, which is just, you guessed it, the square of the multiple correlation. It reflects the proportion of variation in the dependent variable accounted for by the independent variables. We also have an adjusted R square because R square can be positively biased, particularly when you have smaller sample size and larger number of predictors. So this is basically sort of a calibration of the R square value. So and basically R and R square are designed, basically they range from 0 to 1. Now so you can see right here that the set of predictors using R square accounted for roughly 41.2% of the variation in the achievement measure. The f-test is given in the ANOVA summary table right here. So there's the f value and the p value for this. So if this is statistically significant, we would infer that the R square value in the population is greater than 0, and that happens to be the case in this particular data set. As we scroll down, you'll see that we also have, there's our coefficients table right here. We have our unstandardized regression coefficients. The constant is the intercept in the model. It's just basically the predicted value on y when all of your predictors are equal to 0. And given that none of our predictors except for gender ID incorporate a 0 point, it's this really more of a nuisance parameter than anything else. But if we had meaningful 0 points on the other predictors, then this could then that would facilitate interpretation of the intercept. Nevertheless, we see that performance goals, the unstandardized coefficient is negative, indicating that higher scores on performance goals are associated with lower scores on achievement. And that relationship is statistically significant. Mastery goals, there's a positive relationship to achievement. Basically, higher scores on mastery are associated with higher predicted scores on achievement. That relationship is significant. By the way, the significance values, or the p-values right here, are all for two-tailed tests. If you're carrying out a one-tailed test, then technically the p-value would be half this value. And I go into a lot more detail in the PowerPoint on one and two-tailed tests, but like I said, for the purposes of this demonstration and keep it shorter, we're just going to treat our hypotheses as non-directional, which would require a two-tailed test. We also see that interest right here has a positive predictive relationship with achievement, and it's statistically significant. So three predictors right there are significant predictors. Anxiety, there's a negative predictive relationship. Basically, higher scores on anxiety are associated with lower predicted scores on achievement, but that is non-significant. So anxiety is not really contributing to the model. Gender ID has a negative coefficient, and it's non-significant. But if it were, basically what this would indicate, because of the coding system, again, 0 is male, 1 is for female, so the negative coefficient would just basically indicate that females were scoring lower on achievement than males. But that's not the case, because again, we have a non-significant predictor in the model. So altogether then, we can say that as a set, the predictors accounted for statistically significant variation in the achievement dependent variable, but of those predictors, it looks like that performance goals, mastery goals, and interests are largely driving that association. So you can see right here the standard errors are associated with the unstandardized coefficient. This is a t-value right here, which is just formed as a ratio of the unstandardized coefficient to its standard error, and again, this is the p-values right here. The standardized coefficients that are given right here can be useful, particularly for sort of rank ordering the predictors in terms of their relative contributions. So one of the downsides of the unstandardized coefficients is that they are all dependent on the scales of measurement of the independent variables. And so basically the standardized coefficients treat the independent variables and the DV, by the way, as all having a scale basically with a mean of 0 and standard deviation 1. So it's basically treating all of those variables as being standardized, and because of that it makes these coefficients scale free. So then we can take the absolute value of these coefficients and rank order the predictors or the independent variables in terms of their relative contribution. So you can see right here mastery has the strongest predictive relationship, followed by interest, followed by performance goals, followed by gender ID, that's number 4, and then followed by anxiety, which would be number 5 right here. You can also see that we have 95% confidence intervals, as I've said before. This just basically provides an interval estimate for the population regression coefficient, and but it can be used for null hypothesis significance testing. So assuming a non-directional hypothesis, basically the null hypothesis is that the population slope is equal to 0. So if 0 happens to fall between the lower bound and the upper bound, then we would infer that the slope for a given predictor is essentially 0 within the population. If 0 falls outside, either above the upper bound or below the lower bound, then we would infer that the population slope is non-zero. So next we have a set of correlations that are given, including zero order, partial, and part correlations. And so the zero order correlations are basically Pearson's correlations between the IVs and the DV. And the partial correlations, which is in the second column, reflect the correlation between each IV and the DV, controlling for the remaining IVs from both the individual predictor and the DV. So that is kind of a mouthful, but there's a little bit more information in the appendix for this PowerPoint that kind of goes a little bit more deeply into those issues, and particularly referencing the partial plots. Finally, the semi-partial correlations, that's in the part column, and it reflects the correlation between each IV and the DV, where essentially what we're doing is we're controlling the remaining IVs from a given IV. So by doing this, the square of the semi-partial correlation actually gives you the proportion of variation in the dependent variable that is uniquely accounted for by a given independent variable. And so this also can be very useful in rank ordering the independent variables in terms of their relative contributions. So I just kind of took out an Excel file, and you can see right here I've got the semi-partial correlations, which are reflected right here. This is the square of them, reflecting the proportion of variation in Y uniquely accounted for by the independent variable, and then just kind of assign the rank ordering. And you can see it's the same rank ordering that we saw before with the standardized regression coefficients. Finally, in this part of the output, we have our collinearity statistics, which include the tolerance and variance inflation factor. Basically, the tolerance is essentially equal to 1 minus the R-square value where a given predictor is regressed onto the remaining predictors. So, and then variance inflation factor is essentially the reciprocal of the tolerance. So, as a general rule of thumb, for tolerance values, if they are less than 0.10, they might that would be an indication that there's greater problems associated with multicollinearity. With the variance inflation factor, or VIF, values greater than 10 would be considered indicative of the presence of more severe multicollinearity. So you can see in this demonstration that there do not seem to be any problems with multicollinearity among the independent variables. Okay, so here we have our histogram of the standardized residuals, and as I said before, this can be useful for evaluating whether or not the normality assumption has been met. So you can see right here, the residuals look fairly normally distributed. It's not perfect, but what you're looking for is at least reasonable evidence for normality. Okay, here we have the normal probability plot. Basically what we're looking for are the residuals to essentially fall pretty close to the regression line that you see right here. So, and that actually is the case. So that's actually indicating greater evidence of normality for the residuals. So what we don't want to have is a situation where the residuals are, exhibiting more severe departures from the regression line. Okay, so on the left we have our plot of studentized residuals against the standardized predicted values. So in general, we're looking for residuals to be randomly and evenly distributed around 0 and falling between roughly -3 and +3, between -3 and +3 units. So we can also use the scatter plot to identify potential outliers. So right here you can see that case number 46 looks like that's a potential outlier in the data. And kind of going back into the output file, the way I was able to label that, I just went to the output with the studentized residuals and double clicked on this right here. So this chart editor opens up. I can go under elements, click on data label mode, and then I can click on this right here, and you can see what case that happens to be, and that's case number 46. Okay, an assumption associated with linear regression is that you have a linear relationship between your independent variables and the dependent variable, and basically nonlinearities can show up in the residuals plot. So this is just kind of this plot on the left is sort of an idealized plot of, in this case we have sort of a quadratic relationship between the predicted values and the studentized residuals. So you can see right here that that we have this kind of curvilinearity taking place, and there's no evidence of that when it comes to our residuals plot on the right. We're also looking for evidence of heteroscedastic errors. So heteroscedasticity is just referring to the idea that the variance of the errors is non-constant. So to give you an example, and this is one of the more common situations, is where you have essentially sort of a fan-shaped pattern. So you can see right here that as scores increase on our predicted y variable, you can see that we get increasing spread when it comes to the residuals. So in this particular case, this is just one kind of situation. It can also be reversed where things are kind of going in the opposite direction as well. There are more kind of trickier versions as well, but you can have like a bow tie sort of plot and so forth. But basically, sort of the fan shape pattern is one of the more common situations where you might observe heteroscedasticity, and there's no real strong evidence of any kind of pattern of that nature when it comes to our data. I will say though that you do want to be mindful that outliers can produce indications of heteroscedasticity. So to give you an example, at 0 on our studentized residual, I'll just kind of draw a little line right here. You can see that there's considerable distance here, but basically this is associated with a given predicted value. So if we had even a little bit of spread right here, you can see that it might produce some non-normality, but then also you can see that there would be greater spread when it comes to the dispersion of those residuals at that particular predicted value. So that is something to be mindful of. Next, we also want to keep in mind that least squares regression makes the assumption that the residuals are independent of each other. That is, that they're randomly sampled from a population of residuals. And so one situation where this can be violated is when you have data on the dependent variable that's repeatedly measured over time. And so what that can do is produce essentially autocorrelated errors. And so one way to evaluate that, if you have a variable that's kind of measured repeatedly over time or something of that nature, is to utilize a sequence plot. So on the left, this is an example of a sequence plot. It's not using our actual data because our actual data wasn't measured over time. It was actually measured all at the same time. So there's no reason to suspect a relationship between the residuals and time. But so this demonstration over here on the left is just kind of a sequence plot, which gives you an idea about how the residuals are kind of varying over time. Now I do want to bring up that kind of going back here to our studentized residuals, which we have right here for our plot, kind of going back and talking about heteroscedasticity. This is basically the studentized residuals plotted against the standardized predicted values, but it's also worthwhile to plot the studentized residuals against each of the individual predictors, because it may just be one predictor or maybe a couple of predictors that might be producing any kind of heteroscedasticity. So what we can do is actually, since we've saved the studentized residuals to our SPSS file, we can actually use the scatterplot function to plot the studentized residuals against the individual predictors. So let me show you how to do that by kind of going back and opening up SPSS. So you can see right here that looking right here, we have our studentized residuals. So I'll click on this right here to show you. So just to give you an idea about what I'm talking about, we can use the graphs option, go under legacy dialogues, scatter dot right here, click on simple scatter, define. We'll move performance goals, which is one of the predictors, to the x-axis, and then we can identify, it's a little bit tricky now, but identify the studentized residual right here, move it to the y-axis, click on OK, and so now you can kind of visualize the relationship between that given independent variable, in this case performance goals, and the studentized residuals, and look for any kind of weirdness when it comes to the possibility of heteroscedasticities in terms of the errors, or looking for potential outliers and so forth. Okay, so moving on, these are the partial plots that we requested. So these are also referred to as added variable plots, and they're basically akin to the plot of the relationship between the IV and the DV, controlling the remaining IVs from both variables. So it's pretty much analogous as sort of a visualization pretty much of the partial correlation. And so these can be useful for essentially looking for possible nonlinearities between the independent variables and the dependent variable. So you'll see in this particular demonstration, this is performance goals against the achievement variable. And you'll notice that if I kind of scroll back up to the partial plots where we've got performance goals and achievement, by default there's no regression line in there. If you want the regression line, you can just double click in the output and go back under chart editor, and you can click right here where it says add fit line at total, and by default it gives you a linear function. If you don't want the label, you can just kind of click off attach label to line, click on apply, and there you go. If you want to look at different possible trends, then you can basically click on a given trend like quadratic right here, click on apply, and you can kind of get an idea about any possible nonlinearity. So that's basically, here's cubic right here, just to kind of look at that. So these are ways that you can kind of visualize whether the relationship is linear or nonlinear between a given independent variable and the dependent variable. Okay, so here, as I said before, we've clicked on the Save tab and we really saved a number of indices to the data set. If you want to evaluate studentized residuals in order to identify cases that might be considered outliers, you can easily do that using, you can basically either scroll down the data set to identify potential problematic cases, or you can kind of do a screening. So one example might be using the explore function. So let me just kind of go into our data file yet again. So these are our studentized residuals, and as I said before, you can just kind of scroll down, but it's going to be a major pain in the neck if you have a very large data set, and it would be easy to overlook things. And what we're looking for are cases that would have a studentized residual that falls outside of the range of -3 to +3. So if you don't want to just kind of scroll down every one of these, here it is right here. There is that one case, which is case number 46 that we had right there. So if you don't want to have to do that, another option then is to go into Analyze, Descriptives, Explore, and you can basically kind of scroll down here. We'll put studentized residual in the dependent list, and if we click on statistics, we can ask for outliers. So, and by the way, just because you select this as outliers doesn't mean that everything that shows up are outliers. Actually, it's going to show up as extreme cases or extreme values, and just because you have an extreme value doesn't necessarily make it an outlier. So you have to use kind of your judgment. But nevertheless, we can click on continue and then on OK, and now when we look at our extreme values right here, you can see we get basically the highest values and the lowest values right here. And you can see that case number 46 has that studentized residual, which is 3.41. So you can see that that case would be a candidate as a possible outlier in our data. Okay, so finally we have our other indices as well. We have Mahalanobis distance in the first column, Cook's D, DF fits, standardized DF fits. These are additional indices that can be utilized to identify potential outliers on the predictor variable. That would be the Mahalanobis distance, or influential cases, which can be identified using Cook's D or DF fits. I'm not going to go into too much further into all of this, but this can be useful for identifying cases that may be having an effect on the overall regression model and the fitted values. There's also, as we kind of scroll through right here, you can see that we have standardized DF betas, and these are useful for evaluating whether a case is having an undue influence on a given regression parameter. So this is for the intercept, the first predictor, second predictor, so forth, all the way through the fifth predictor right here. And so you can kind of, basically what you're looking for are values that are greater than 2 in absolute value as potentially having an influence on a given regression parameter. So the long and short of it is that you can use the Cook's D, DF fits to evaluate the effect of a case on the fit of the overall model and the predicted values or fitted values, whereas you can use the standardized DF betas to identify cases that may be having an undue influence on individual regression parameters. So at any rate, there is an appendix, as I said before, in our PowerPoint. So be sure to check it out. And also be sure to check out the references and resources at the end of the PowerPoint as well. So that concludes this discussion, and it's a little bit longer than I was expecting, but there was a lot of territory to cover. So I appreciate you watching. Again, if you find the video and the information useful, please like the video and share it with others. Thanks again for watching.